Hello, this is Professor Robert Needham. Welcome back to Math 068. This is going to be for us section, 13, scientific notation. In scientific notation, really what we're going to cover is how to write numbers which are incredibly large and incredibly small. This really shouldn't be a difficult chapter for us. And you could use just a standard scientific calculator or a standard calculator. You could use a graphing calculator or you could use Desmos. You could use any of those particular ones and we'll get the job done just fine. So when we talk about the definition of scientific notation, it's a way of writing a very large or a very small number. By very large, we mean something, for instance, that has 12, 13, 14, 15 zeros at the end of it, or something that's a decimal place that is out 13, 14, 15, 16 positions. It has nothing to do with being positive or being negative, okay? They give us a nice example here at the very beginning, and in this particular example, they say, how would you write, and they give us this incredibly large number for kilograms. And first of all, just to simply work with this is just so cumbersome that most people would lose track of the zeros, lose track of the value. I mean, you're out 1, 2, 3, 4, 5, 6, 7, 8, 9. You're out 3 times 9, 27 zeros at the end of a 1,988. So it's very, very large, okay? But we have a way of writing scientifically in such a manner that we can have the same number written meaning exactly the same thing. And we'll talk about how to convert back and forth today. If we talked about the mass of the Earth, for instance, the mass of the Earth is 5.972 times 10 to the 24 kilograms. And that would be the same in what we would call standard notation to write it this way. There's a clear comparison between the number on the exponent and the number of values to the right-hand side of the 5. And we'll have that discussion here in what we're talking about. Writing a scientific number. To write a scientific number will always fall into this particular form. N times 10 to some exponent A. It says where N is a number between 1 and 10, so it can be no smaller than 1. It cannot be a 0, nor can it actually be 10 itself. It has to be between 1 and 10. It's allowed to be 1. It's not allowed to be 10. Another way I like to say that is it's a single-digit number, where A is some integer, and that integer can be positive or negative integer. Now, it goes on to give us a long set of rules here, and I'm not quite sure I'm going to be a fan of rules, but it says to convert a number from standard notation to scientific notation, that we move the decimal point in your number until there is only one non-zero digit to the left of the decimal point, resulting in a decimal number n. Okay, I'll show you how to do that. 2, count the number of decimal places you move the decimal point from the original number. This will determine the value of a, the exponent. So counting the movement is what we're going to do in order to get the a value. Step 3, I'm not a fan of. If you move the decimal to the left, a is positive. If you move the decimal to the right, a is negative. I'm going to show you what I think is a better way for that. So for example, and they give us a couple of numbers here. They say that if we started with a standard number, and I'm going to switch over to my document camera because I think I could do a little bit better job of pointing this out on a full-size doc camera. And it's turning on. Here we go. Now, so what it tells us, if we start with this full-size number, first of all, I'm going to give you a couple of hints. One, this is a very large number. And by large, you're going to think I'm crazy. It's greater than 1. Okay? It's greater than 1, so therefore to me, when we started here, this number is large. This number over here is less than 1, so for me, this number is small. And I'm going to show you where I'm going with that in a moment. So what we do is we take the starting position of the decimal and we move it until it's between the 3 and the 2. Why there? Because if you left it here, it would be 32, and if you put it back here, it'd be 0.3. Remember the directions. This number has to be between 1 but less than 10, and 3 is the number that does that. And then we count 3, 6, 9. 9's important. So we moved 9 units from here to here. So now we have a new number, 3.25. Notice we got rid of all of the zeros, and we just kept the 3.25. We moved 9 units, which becomes the exponent, and they tell us because we moved to the left, it's positive. I'm going to tell you because it's large, it's positive. Any number greater than 1 will carry a positive exponent. On an example over here, we have a number which is really small. Well, you can kind of guess this thing's going to carry a negative exponent. I don't really care which way I count. I take my decimal and I move it over until it's on the right side of the 4, because I need to have 4.0 or 4. And if I count from here to here, that's 7 units of movement. 7 units of movement to the right, or because it's a small number to start with, will give me a negative exponent on that movement. Let's try some examples. Convert each of the following numbers to standard. From standard to scientific. We want to take it out from what we normally write it and turn it into scientific. We find the original decimal point, always at the end of the number unless otherwise seen. We move it in between the 5 and the 2. We keep 5.268. First of all, this is a big number, so I know right away the exponent's positive. I moved 1, 2, 3 positions. So it turns into times 10 to that positive 3. I go over to this value, 0.000689. Well, I have to move it until it's right here between the 6 and the 8. So this turns into 6.89. I check the movement. The movement from here was 1, 2, 3 times 10. But remember, this is a small number, so it's minus 3 on the exponent. Now, the reason I like this is because it always tells me what to do if the number is greater or smaller, and it's very easy to tell if a number is greater or smaller than 0. Now, if we're converting in the other direction, so it says convert a number from scientific notation to standard. Well, it says the exponent tells you how many places to move. We know that, the letter A. If the exponent is positive, you move the decimal to the right. So see, now all the directions change. But if you think the way I think here, positive means make the number bigger than 1. Negative means make the number smaller than 1. If you give me a number, 3.25, and you tell me it's a positive exponent, I know the decimal has to go to the right. How do I know it has to go to the right? Because if I move it to the left, the number will be smaller than 1, and this is a number which is greater than 1. I know that because it's a positive exponent. So I would move that decimal 9 positions, 2 of them just to get to the other side of the 5, and then 7 more, and I would fill those in with zeros. If the number is a negative exponent, I know I have to move wherever the decimal is at currently, which is on the right side of the 4, to the left 7 times. Why left? Because it's a negative exponent, and negative numbers go left. I would take and move once to get to this side of the 4, and then 6 more zeros, and I would fill in those values of 6 zeros right there. So let's try that. We have an example of 7.21 times 10 to the 3. Right away, the number has to be bigger than 1 when I get done. Positive numbers move to the right. So I'm moving 1 position here, 2 positions here. I need a 3rd position, 7,210. I don't have to actually put a decimal there because I moved it to the right and ended it after the 0. I filled in the 0 because I had to move more places than I could move. I have a negative 3. That's going to mean a left movement. Now, if I move once here, I need 2 more. So I need to fill in 2 positions with a 721, and I like to put a 0 right there just to show this number is smaller than 1. Scientific notation is incredibly straightforward and incredibly easy. At the bottom of this page, it says most calculators, including TI-83 and 84, will automatically express very small and very large numbers in scientific notation. The scientific notation on the graphing calculator looks a little different than we have been working with so far. If you are using a graphing calculator, you will see a bit of a difference. And I will open that up just so I can simply show you what that looks like. Again, I will also show you simply using Desmos and how Desmos will interact with you. Most graphing calculators will spit back what's called an E-value. And an E-value is scientific notation, shortcut in graphing calculator world. Let me clear what I have here. And second, let me quit it. And let me clear out. Okay. So let's say that I'm going to enter one of these very, very large numbers. So let's say I'm going to have 2.5. I'm going to do times 10. I'm going to raise that to an exponent. And let's just say I'm going to raise it to the 21st. So that way it won't make it into a regular number. So this is scientific notation for 2.5 times 10 to the 21. We know it's a number bigger than 1. It'll move the decimal 21 positions to the right. If I hit enter, notice it says, hey, this is 2.5 E. E stands for times 10. After the E is the exponent of 21. If I did this with a small value, let's say 1.4 times 10, and I raise that, let's say to a negative, let's go 17 this time. It'll do the same thing. And notice it removes or strikes out the times 10. It's redundant because E means that value. If also, if at the same time, if you put in a number which is very, very big, I fill up a screen with something and I hit enter, it's going to convert that to scientific notation for me and say, this is too many decimals. We don't need to have these. Let's go scientific. Now, Desmos is similar to that, but Desmos is not exactly the same as that. Desmos doesn't spit back E values. So let's say that I enter something in Desmos, and let's say I put in 1 times, I'm going to do 10. Remember, we can raise anything in Desmos to any kind of exponent. And I think, well, if I just put a square in, notice 100. But no, watch what happens if I make it a 22. It changes it into scientific notation automatically. If I enter a number that's very large, notice that it won't change anything at all because it says, okay, fine, I can keep those many decimals. I'm going to hang on to them. It will not convert them into this format. You have to do the converting. But at the same time, it does everything we need it to do. And you can also do this with a standard $8 scientific Texas Instruments scientific calculator. Let's go back to where we were. Oops, I'm jumping all over the place. And here's the example of what it looks like, and I just showed that to you. Write each calculator display number in scientific notation and in standard notation. All right, so I'm going to flip over, and we're going to do these together. So let's do exercise number letter 3A. So first of all, it says we're supposed to write this in scientific. Okay, well, I know this means times 10. So it's going to be 5.697 times 10 negative 4. There's the scientific. Standard means get rid of all of this. Negative exponent, move to the left. One position here, and I need 3 more. So I need 1, 2, 3, 5, 6, 9, 7. And I'm going to put a 0 right there. E4, positive number. I'm going to, first of all, rewrite 5.697 times 10, and 10 will raise to the positive 4. I'm going to move 3 positions here, and then I'm going to add a 0. 5, 6, 9, 7, add a 0. Student exercise number 4, and I am probably going to leave a couple of these for you to do. In a hypothesis test of whether mean IQ score for children whose mothers smoke 10 or more cigarettes a day during pregnancy is or not the same for those whose mothers who do not smoke. The p-value was found to be 7.21 times 10 to the negative 3, while the alpha level was 0.01. How does the p-value compare? Okay, so we're trying to compare a 0.01 to this right here. Actually, I should have this one first and this one second. But we can leave them in the space for right now. So let's convert this p-value. I'm going to move this p-value over here because it says p-value and alpha. I want p-value first, alpha second. So I'm going to move this 3 positions. Negatively means to the right once, and I need 2 zeros. 2 zeros, 7, 2, 1. So once, twice, 3 times, and I like that 0. And I'm comparing that to 0.01 or 1%. Okay, compare. First decimal place, even. Next decimal place. Okay, well, this one has a 1, this one has a 0. That makes this one bigger. That tells me that the p-value is less than the alpha value. That will be very meaningful to you. In a hypothesis test of whether rates of quitting smoking are significantly higher, anytime you see that, you're going to see a p-value. Using a nicotine patch than using a placebo patch. The p-value was found to be 5.697 e -4, which means 5.697 times 10 to the -4 if you desire. However, though, ultimately what we want is the decimal, so we're going to move this thing 4 to the right. 1, 2, 3, 5, 6, 9, 7. We're comparing that to an alpha level of 0.001. How does that compare to 0.001? Okay, we'll compare the decimals. In the 10th, there's zeros. In the 100th, there's zeros. We get to the thousandths, this one's bigger. P-value is less again. So once again, p-value comparison is p-value is less than alpha value. I'm going to leave student exercise number 6 for you to complete as part of your upload. Hope that helps you. If you have any questions, feel free to email me.